Hello everyone, I'm Bhavin Chakshi and today I'll be talking about building robust deep neural networks using principles from neuroscience. Convolutional neural networks have really caught up to humans in the last decade on difficult tasks such as classification. Still, a small perturbation in their input, which generally a human won't even notice, causes egregious classification errors. Even naturally occurring noise can reliably force networks to misclassify images. Hence, we ask if we can employ brain-inspired strategies in machine intelligence to make them more robust. We start with predictive coding, a prominent theory in neuroscience. Predictive coding posits that the brain actively predicts the world it sees and then uses the errors made in the predictions to correct its internal model of the world. Now for the machine implementation, we start by passing an image through a pre-trained feed-forward network. We then add feedback connections and train them to make predictions using the representations. The representations are then updated with the following equation with 4 terms. The feed-forward term that prevents disconnecting from the world outside, the feedback term that allows top-down influence, a memory term, and the error correction term directly based on the idea of predictive coding. All the coefficients are treated as hyperparameters and the weights are fixed during iterations. For our experiments, we use a pre-trained VGG16 as the feed-forward network. We select 5 layers from the network and treat them as encoding layers as per our equation. Since we want to use the feed-forward VGG as a baseline for comparison, we fix the feed-forward weights and only train the feedback weights for the reconstruction objective right after the first feed-forward pass. We first measure the accuracy of the network across time steps. On the right, we see that the baseline accuracy on clean images doesn't change much. But in the presence of Gaussian noise, the proposed dynamics help the network to regain some accuracy. We also investigate the reconstructions made by the network for these noisy images. As can be seen in the middle plot, the mean squared distance between the reconstructions and the clean images decreases over time steps. It is worth emphasizing here that the network is bringing these reconstructions closer to the clean inputs without ever seeing the clean images. To investigate the evolution of higher layer representations, we pass the clean image and a noisy image through our network and calculate the correlation distance between the representations obtained across the network for all time steps. To compare with the feed-forward VGG, we normalize all the distances such that VGG is always at the distance of 1. On this plot, you see that for a wide range of noises, the correlation distances decrease across time steps for all the blocks of VGG. That is, the network iteratively projects the noisy representations towards the clean ones. This is an important property for robustness because every time the model encounters a noisy representation, it will try to take it back towards the learned representation manifold. We now use ImageNet-C, a comprehensive dataset with images corrupted with 19 different types of corruptions at different severities to benchmark the robustness of our network. We calculate the mean corruption error scores across time steps and normalize them with the score obtained for the feed-forward VGG. On the right, we see that the MC score decreases over time steps, showing that the dynamics brings more robustness. We also use a suite of adversarial attacks to measure robustness. On the plots here, we can see that the median perturbation required by the attack to successfully fool the network increases across time steps, again demonstrating the robustness of our network. In conclusion, in this work, we propose a predictive framework inspired by neuroscience and demonstrate that it helps in projecting both noisy reconstructions and representations towards the clean manifolds. We employ a dynamics and standard feed-forward network from the field and show that it leads to improved robustness against natural and adversarial noise. Thank you.